Hello guys, welcome to the class. And few people are here yet. David, can you hear me?
Yes, I can hear you.
So today is last class actually. You can see the share screen?
Yes.
Yes, sir.
Okay. So today is the last lecture actually. So the next week I will have some little kind of, it's not exam, kind of evaluation. So today's lecture basically on not very long, it's short kind of, focus on the diagnostic, that how can you make a measurement, because femtosecond pulses are very short pulses. So it's not easy to make this kind of measurement easily.
Did you have start to recording the presentation?
I didn't even start my lecture yet.
Okay.
Okay. Okay, so is it live somewhere, David?
Yes, on YouTube.
Okay. How many people are here? Tahura Hadi is here. Salman is here. Can you hear me, Salman? Zanfar, you cannot be on time. You're 5 minutes late again.
Awesome, sir.
Sir, I have
What's-
no link.
No link of what? With whom?
I asked
Net.
from the David. Yes.
Okay. Yeah, because you are detained student, so how can I be?
Hello, sir.
Yes, but where are you?
Sir,
So if
Salman
you
here.
get, yes, I know that. But if you are planning to quit the class before time, then you will be considered failed. Yes, Salman?
Whom? Me, sir?
You.
No, sir. I am not quitting, sir.
Who
I
knows?
just joined, sir. No, sir.
Mhm. So how is the weather, by the way, in your region, Salman? Where do you,
Minus
you
2 degrees
teach?
centigrade.
Okay. So
Minus
it's
2
similar.
degrees.
Yeah, it's a similar like where I'm sitting here now.
Oh, they are also.
Yes, definitely.
Uh-huh.
Okay, so today actually happy day for many students like Salman because it's the last one. The next week, yeah.
No, sir. Actually, on within 2-3 days, we will be having vacations for 4 months, inshallah, for the next 4 months.
4 months vacation?
Yes, sir. From December to April.
Really?
Yes, sir.
It's a long vacation. It's because of the cold weather there? Yes?
I didn't hear you.
Is it because of the cold weather?
Hello.
Snow falling? Salman, your net actually is always having a problem. Okay, so
I'm
yeah.
listening now.
Yeah, what I'm saying, it's a cold there. That is why they close for 4 months.
Yes, exactly, sir. It's too cold for the small children from class 8 to 12th class.
But in
And we
your
have covered all the courses.
okay, so but it
They'll okay, sir.
no, what I'm saying, do you teach to small kids?
Yes, sir. I teach to first year and second year.
Okay,
11th grade and 12th grade.
but it has lower grades as well.
Exactly, sir, as compared to BS and MS.
Okay. Okay, so today not many. Okay, Marishi is here now, and Rusa Hadi and Tahura Hadi. Okay, so I'm going to start now, but this lecture is dedicated to the diagnostic, and diagnostic mean how you can measure such a small pulse, such a short pulse, not small actually. So it's not. I don't go into much detail because of most of the students here, they don't have in-depth knowledge of things related to the ultrafast yet. But it's good for them to know from this lecture. Okay, so okay, you know the peak power. Peak power is I taught already actually, but like what is the power at the peak? Okay, simple words, the peak power. Because when we say or when we discuss the pulses, then it means we consider the power at the peak of the pulse. Okay, so another pulse is coming, maybe another pulse is coming. Okay, so what is the power at the peak? And we can also have an average power. Average power mean something like in this range or something like this. But that is not very, I mean, it's not a correct measurement, you can say. Whenever we deal with the pulses, you have to consider the peak power and then energy. Okay, so what do you see here? This is a simple formula. Pulse energy over pulse duration. Okay, so pulse energy over pulse duration. Pulse energy we can measure with any kind of power meter or energy meter. But how to make measurement of pulse duration? So if you see here that pulse energy, we can have power meter, energy meter, okay, commercially available, okay. And then how we can make measurement with the pulse duration, okay. So the peak power, when we work with the femtosecond laser, it means the peak power is very high in most of the cases. And if you have one amplifier, one or two amplifier, it can go to the terawatt. Very, cannot say easily, but usually it goes terawatt region. So if you have energy, you can see here like 250 joule, and the pulse duration is around 25 femtosecond. And let's suppose if you have a energy of 25 joule and 25 femtosecond, and if you have energy 2.5 joule, 25 femtosecond. So 25 femtosecond is the pulse duration. How did you measure this pulse duration? That we will follow the next slides. But here I just want to show you that if you have a 25 femtosecond, which is the, you can say it's conventional, not conventional actually. Usually, whenever we make a simple, not a simple, conventional femtosecond laser system or ultrafast laser system, then it's 25 femtosecond you can get usually. If you align properly the compressor and stretcher and the oscillator and everything, then you can get 25 femtoseconds. So this one, 2.5 joule energy, probably you can get with the one or two amplifier, simple homemade kind of femtosecond laser system. And if you have a 2.5 joule, then you can easily get 100 terawatt. Okay, and it's a huge power, the peak power. Okay, and if you increase the energy bore, you have more passes a little bit in the amplifier. So then you can have like 25 joule and 1 petawatt. You can go up to 1 petawatt. And after that, if you have huge system, many stages of amplifier, you can go up to 250 joule, which is a huge energy. Okay, and it's 10 petawatt. 10 petawatt means, I mean, it's a huge kind of energy, and it's not easy to control as well and to detect as well. Different things.
But sir, 10 petawatt is less than 100 terawatt, I think.
No, no, no.
No, tera is
Check.
10 is to power 18 and peta 10 is to power 15.
You check it. I don't know now.
Okay. Let me check.
Okay, so if you just convert, let me check, 1 petawatt.
10 is to power 12. No, tera is 10 is to power 12.
Yeah.
And peta is,
So
okay, peta is more
yeah,
than.
yeah, it's more than 2 because 1 terawatt is equal to 0.001 petawatt. So it's definitely
Yes,
is
sir.
huge. Okay. So petawatt actually, there are few systems in the world, I mean, which can generate the petawatt power. Okay. Mostly in the university labs or other institutes in West Europe and in America and some other places, mostly in America and Europe. They have like terawatt is very common in the universities. Okay.
Uh,
When you go to the petawatt, that's David, you want to say something? Do you?
yes, for example, in the National Ignition Facility, laser center in San Francisco, United States, have 500 terawatts. Is
Yeah.
for initiate nuclear reactions.
Yeah, that is for the fusion kind of stuff. So yeah. So petawatt, when you move to the petawatt is not very old. I mean, it's like last 10 years or maybe 10, 15 years, people started working on it. And the petawatt, there are few facilities which can generate the petawatt. And one of the facilities are extreme light infrastructure, all the 3 facilities. And in America, definitely. And China is trying to reach to up to 100 petawatts. UK is building the system for 20 petawatt. And about the US, I don't know. But China is really trying to go to 100 petawatt. Okay, so now the main question here, 25 femtosecond. Okay. How did they measure 25 femtoseconds? Femtoseconds measurement is not possible directly. Nanosecond you can measure with the oscilloscope. Okay, if a good oscilloscope is there, you can. But in case of femtosecond, it's not possible with the oscilloscope. You don't have such a high efficient and such a bandwidth oscilloscopes. Before to go further, I would like to mention this guy. He's called Trevino. And he's a pioneer in the sense that he introduced the most reliable diagnostic techniques, especially for the ultrafast lasers. And he wrote a book as well. This is it's called Frequency Resolved Optical Grating Frog, Measurement of Ultra Short Laser Pulses. So I took slides, some of the slides. He's from Georgia Tech. And he has spin-off, like he commercialized this diagnostic system, which is called the Frog, Frequency Resolved Optical Gating, and some other things related to this system, like software and etc., etc. So he's a pioneer kind of guy. And why I'm showing here this guy, because I use some of his slides. And it's a good people to know that to generate femtosecond pulses is not that much troublesome maybe, but to confirm that this is really femtosecond pulses or ultra short pulses, this is the important thing. Okay, so you cannot claim that what system you had made, it is generating a femtosecond pulses. Okay, so that is why measurements are very important. Okay, so here how we can measure the ultra short pulses. because it's the very shortest event, okay? So how we can make, or we can measure the shortest event? Hello, can you hear me?
Maybe we can use a grating
Some-
for stretch the pulse.
No, wait
Oh,
a bit, wait a
for
bit. There is some problem with your Zoom actually. Wait a bit. You can see the sharing now?
no, not now.
No, yeah. How about now?
Yes, we can see.
Just a minute. Okay, so you people can see now?
Yes, we can see.
Okay. Okay. So you were saying something, David. Say it again.
Uh, Maybe we can use a ultrafast diode for capture, but with
No,
a
it's not
diffraction
exist.
grating.
No, not directly. It's not possible directly
But with
because it's
a
rise time.
diffraction grating like the CPA method to broad the pulse.
No, if you brought the pulse, I mean, you cannot make then it will give the measurement of the broad pulse. Okay.
Okay.
See
Sir,
here. Hmm.
sir, we can use the autoclave, I think.
Auto what? Say it again.
Autoclave.
Wait a bit. Maybe you are missing one word actually. Okay. So shortest event, a femtosecond event. Okay. So why this animation is not working? Wait a minute. Yeah. So femtosecond actually is shortest event. And to measure this shortest event, we need to have a shortest event. Okay. But how can we have shortest event? So that pulse itself. Okay. So pulse itself means, if you see here, this word or sentence actually, not a word. Here. And what we have here, we have the pulse itself. Okay. So what we do actually, we use a non-linear crystal and in non-linearity. Now, what is non-linear crystal? This is also a long story. Who knows about the non-linear crystal?
I know little about the nonlinear crystal.
What is non-linear crystal?
I use the photorefractive crystal. That is a crystal that can change the geometrical internal configuration. In this case, with a nonlinear crystal, we can generate the second harmonic generation, and also is used for a camera when you work with a laser of femtosecond laser to don't blink the sensor. Okay.
Okay. So you are right, I mean, somehow. And who else know about the nonlinear crystal? Because I didn't go in detail, I remember, but I mentioned this thing actually. Nargas, do you
Sir,
remember? Wait a bit, Zanfar. Nargas.
What do I remember? It was about the refractive index. Means it changes the refractive index with the intensity of light.
Refractive index. In other sense, actually, not exactly. Okay, Zanfar, you.
sir, my answer is also same. When some intense light fall on crystal, it changes its intensity. It's a refractive index.
Intensity definitely changes, but it's a non-linear crystal actually. Some other non-linearity is also happening. So let me ask some other guy. So how about Adnan? This guy comes and then goes. And at the end they say, okay, net problem. Salman, do you have idea about the non-linearity? Non-linear crystal?
Sir, I have a little bit idea about it. That actually, when a light pass from a non-linear crystal, so it change its frequency and phases.
Yes, frequency definitely. Okay,
Yes,
so
sir.
who else? Yeah, who else? Tahura Hadi.
Actually, we use it for to convert the frequency or wavelength.
Yes, you are right. But let me ask some other people. Tahura Hadi.
Yes, sir, I don't know about.
But I mentioned in the previous lectures, I don't know which number lecture. And how about the Urusa Hadi?
So she is in the class, I think. Assalamu alaikum, sir.
Walaikum salam. So Arusa, what is nonlinear crystal?
Yes. Sir, it combine or split frequency, input frequency. It produce integral multiple of input frequency.
Okay, somehow, but not very clear. Amna Said.
Can you hear me, sir?
Yes, sure.
Sir, I don't know, but a non-linear crystal must be a non-linear material, and so it would have a non-linear response of polarization with the electric field.
Ali. Ali, are you there or are you attending the wedding ceremony?
Sir, I'm here. I'm here.
You finished your wedding?
Sir, no, sir. I just came for. Sir, non-linear optics. It uses optical glass which changes the frequency and wavelength and other geometrical properties of light and electric and magnetic field.
That is also, I mean, if you see the mathematical, but you are right. Changes the frequency definitely, but it's double the frequency. Okay.
Yes, sir.
So we use this crystal and so that we have we can have a double frequency. It means half the wavelength. And how do we use this one? We will see in the next slide. What is written here? The pulse gates itself in a nonlinear optical medium. So this word gating Okay. Let me go to the next slide so you can understand more maybe. This is the basic setup. Basic setup of the measurement of the femtosecond or picosecond, even also ultra short laser pulses. And this is called, the method is called autocorrelation. This is what Gazanfar was trying to mention, isn't it?
Yes, sir.
So correct yourself. Autocorrelation is a method, and this device, when you build it, is called autocorrelator. Okay. And what do you see here? This is your input pulse here. Okay. And this is called the beam splitter. Okay. It's a 50-50 beam splitter. So 50% light will go in this direction and 50% light goes here. So this 50% light will be going to this portion, and 50% light goes directly. Now, what is this portion? Gazanfar, what is this portion?
Sir, which one, sir?
This one here.
Sir, this is used for the path length.
Yes, but it's a delay line, isn't it?
Yes, yes.
Okay. So this is this. If you see here, these arrows are showing that it can move forward and backward. Okay, this rectangle kind of thing. And there are two mirrors on it. So it means these mirrors are also moving. Okay. So half of the light will go to the delay line and half of the light go directly to this nonlinear crystal. Okay. And what happened? It means it has two arms. After the beam splitter, 50% here and 50% there, the laser light or the laser beam, it moves from here to here, and other part, it moves from here to here. Not here directly. Okay. So after the beam splitter, the laser beam travels in this setup, and it should cover the same distance. Like from here to here, from here to here, and from here to here. Okay. So what we do here, that is why we are using this delay line. Okay. And this delay line is adjustable. We change to and fro so that to make the path from this beam splitter to the crystal and from this side of the beam splitter to the crystal, so that to have the same path difference. Okay, so in this case, when the beams enter in this nonlinear crystal to interfere, and after proper interference, they to have another frequency, which is double the frequency of the original one. If it is 800 nanometer, then that will be 1600. No, this is wavelength. So wavelength will be half, frequency will be double. and wavelength will be half. So wavelength will be here around 400 nanometer. Okay. And you will not see this 400 nanometer until and unless the distance from here to here and from here to here is same. Okay. So this concept, if you see, is called the gating. You move the translation stage and you make possible that both the beams to overlap properly at the same time here. And then we can observe this 400 nanometer, and this 400 nanometer will have information of the pulse. Okay. So definitely information of the pulse mean from this one we can make some measurements. Okay. Definitely the other one, this pulse is 800 nanometer and it has short pulse, whatever it is, 25 femtosecond or whatever it is. But for the measurement, we need this 400 nanometer. Okay. Now, one thing is mentioned here, measuring the intensity and phase with time or frequency. We skip the phase here yet. Okay. We are discussing here simple autocorrelation. Okay. And whatever the green signal comes here, not green, actually it's bluish. This is the detector. Can be a photo detector. Okay, simple photo detector. And it's possible you can use some other detection. You can use a CCD camera. You can use a spectrometer maybe. Simple way. And then whatever you get from here, definitely this light will convert and it gives the information about how much voltage level will be there. Okay. So we can see on the oscilloscope, okay, the photons are converted to the voltage here.
Sir,
Now,
it's
yes, yes.
sir, this work on the same principle of the Michelson interferometer, I think.
Yeah, Michelson interferometer is same, but in that one we only see the fringes. We don't use any kind of nonlinear crystal.
Yes, yes.
Both the arm's length has to be same. This is okay. So we can also make this arrangement like a Michelson interferometer, but to use the nonlinear crystal at the end.
Sir, sir, how we can measure the goal of ours is to measure the pulse duration. So how we can we take some reference pulse, then we compare
Yes.
them and
Yes, yeah, you already studied probably, that is why. We take the reference, we plot. I'm going towards that one slowly, but you are so impatient, I think. Isn't it? So
no.
I'm going towards slowly.
Okay.
So
Okay.
you will see. Here is a nonlinear stuff, nonlinear crystal. You can see, you can understand here. Yeah, this is your fundamental. It's called the fundamental, which is 800 nanometer in our case. And this is your nonlinear crystal. Okay. Nonlinear crystal. And this nonlinear crystal actually can produce, because of its geometry, because of its fabrication, this 2 omega. 1 omega will always be there. It's not stopped. Okay, it will also there. and 2 omega. So it will have two wavelengths now. One is the fundamental, other one is the second harmonic. Second harmonic means half of the fundamental. Okay. And this is your vector. It's a propagation vector, or there are, I skip from here because I don't use that equation here. Okay. But this one you have to keep remember. Okay, so fundamental, pass through, and we get half of the fundamental as well as half of the fundamental. But the intensity will be reduced. Okay. And if you see the equations now here, what these equations are showing, this is the electric field. Okay. And this is the main signal, second harmonic generation. Okay. And time and delay time. Actual time and the delay time. Delay time means passing through the delay line. Okay. And it's directly proportional to the electric field and to the electric field, this one, which is delayed. And this one is the actual electric field. This one is delayed. And passing through here, this portion, this is delayed. Okay. And same if you convert into the intensity, because it's proportional to the intensity. So same thing, intensity of this and intensity of the delayed pulse. Okay. Now, detector. Detector, as I mentioned, that it can be a photodiode, photomultiplier tube, it can be a CCD camera or whatever it is. So detector, now the technology, I mean, much more advanced. You can have much better detectors. Before it was much slower, with a much slower response time. Detectors were available, but now you can have better. So detectors are basically they detect the photon and convert into some kind of signal. And that signal we can see on the oscilloscope or using other kind of needle type detectors or whatever it is. So they emit the electron here, and these electrons are basically current. Okay. So if you see here, here, this is emit the electrons in response to the photons. Okay. Photons are falling on it, and in response we are getting the electrons, and these electrons are basically, flow of the electron basically is current. Okay. So you can make some measurement and you can see some current. Okay. So most of the detectors you can see David's the share screen.
Yes.
Yes,
Yes,
yes.
we can see.
Okay, there's some problem with the Zoom. I don't know. Here from my side, I don't know. Anyway, so if you see here the detector, and it's so slow. Very slow fall time. Response time is very slow, 1 nanosecond. So 1 nanosecond, if you have a detector, I mean like this, 1 nanosecond, definitely it cannot measure the picosecond and femtosecond stuff. Okay. So we have to make some indirect measurement. That is why we're using the autocorrelator. What we see here in this equation, that detector is directly proportional to that current, integral of the current, okay? Whatever the value from the initial to final or something like this. So whatever voltage we are getting at the output of the detector, and that is proportional to the pulse intensity. Detector is not giving any information about the laser pulse. Detector is not giving any information about the laser pulse, but it gives, we can get the information about the intensity from there. Okay. So because we are getting the voltage, and that is, if you see on the oscillator, you can see the different intensity levels at different voltages, okay? So what we do now here, before to do something else, you need to understand the delay line. What is this delay line is showing? As I mentioned that we are using 2 mirrors here. Okay, and this on the platform, these 2 mirrors are on the platform which can move to and fro. Okay. Now, this is the arrangement, okay? Input pulse is coming after the I don't know what is the problem here. Anyway, so here the input pulse is coming here, okay, and the output pulse is going here. This is your input pulse here. That is your output pulse there. Okay. Now, what this translation stage is doing, this mirrors, or the pair of mirrors actually, when you move forward or backward, so we assume that it covers the distance L. Okay. And okay. Now, L is a distance, okay? And T is a time. And C is a speed of light, okay? So we know the simple formula from the high school or something like this. Okay, S is equal to UT, VT, or whatever it is. So this one you have speed or velocity, whatever. This one you have a distance covered, and this one you have a time. Okay, so this is similar kind of equation. Okay, so L is here S, and U is here C, and time is here like tau. Okay. So the time is equal to 2L over C. Why? From where the 2 comes? Because there are 2 mirrors. Okay. So it means not only 1 mirror, 2 mirrors. So there is a factor of 2 is multiplied with this overall time, overall distance, you can say. So it's twice the distance covered. Okay. So this is the delay line. This is the delay line. So we need to calculate when we move this translation stage, then we need to calculate the time, okay, from this one, from this formula. So L, we can make some measurement with the screw gauge on the translation stage. And from this one, you can calculate the time. And this time is very important for the pulse duration calculation. Okay. So you calculate the time from the translation stage. You take the intensity output from the detector. Okay. You have two parameters now. You take the intensity from the detector and you calculate the time from this delay line. Okay. This is the purpose to use the delay line to calculate the time. And after that, when you calculate, you have to plot. But before to plot, you need to understand more. Like this one, if you see here, this is your input. Okay, this is your input. This is the beam splitter here. Okay, and if this is the beam splitter here, it split the beam 50% here and 50% on this side. Okay, so 50% move from here to here and here. Okay, and 50% move from here, here, and it enters the delay line. Okay, and from here it moves here to here, and both overlap each other, and then you get the second harmonic generation. But condition is the distance from here to here and from here to here has to be same. Then you see the second harmonic system. Okay, and what you see at the end, detector is giving some voltage values. Okay, that is intensity. The formula for the autocorrelation is this one. This voltage, what we are getting from the detector, is directly proportional to this autocorrelation signal. Say square, okay, this is a mathematical term, you can also check, is equal to the integral of intensity and delay intensity. And they are integrated over time. Okay. And this is second order autocorrelation because you can see the two here. Okay. Now, we have these things. Intensity we are getting from here, and we make some measurement from this delay line, which is tau. We move further, but before to move further, you can see how it happens. It's a rough kind of animation. You can see overlap here, and then you get the beam at the output. Okay, again, you see one beam is here, it's splitted up. One delay line and other one is here. They both reach here at the same time. And then we can have the second harmonic signal. So basically this arm and this arm should be equal to each other. Okay, this is a rough kind of animation, so it doesn't seem equal. But the distance from here to here and here to here should be same. But it visualized, so you can see that what exactly autocorrelator is. Okay, so they reach here, this point, at the same time. Now, yes.
As your distances are same, so there must be no path difference.
Yes. There is no path difference. There should not be path difference, but we are not saying about the path difference. There is a time difference.
Okay, sir.
Okay, so yeah.
If they have the time difference, then there must be path difference also.
Yes. So, what do you think about it?
Sir, if both pulses reach at the same time there and both have same speeds,
But one pulse,
so
yeah, one pulse has to be a little bit delayed.
so there may
We are
be
saying
path
about the time. We
difference
are saying about
also, a constant pulse,
temporal.
the lambda
Temporal.
also.
No, we are saying about the temporal,
Mhm.
not the special. Temporal. Okay.
Temporal.
Yes.
Mhm.
So
Okay, sir.
temporal. One pulse is temporally
Time.
delayed. So that is why there is a time delay, but not the delay specially.
Mhm.
Not in the space, in the temporal delay.
In the
Okay.
time domain.
Yes, you can think about it. Okay. Now, this is the same thing which I explained actually. What you get here. Crossing the beam, nonlinear crystal, we get this one, second harmonic signal, okay? And varying the delay and measuring the signal, pulse energy with delay. Pulse energy mean here, it's intensity actually. And this is electric field. This is your intensity. This is the basic formula of the autocorrelation. Okay. Second order autocorrelation. And now maybe you can understand more here. When it crosses, then you get this beam. Okay. But temporal overlapping, we adjust temporal overlapping with the translation delay in the time domain. Here you can see the spectrum. Okay. So just a minute. Here you have spectrum or temporal. Actually, it's a time domain. Keep remember, it's not in space. It's not special. It's a time domain. Okay. This is intensity of the seed one. This is also intensity of the seed one, but delayed. But delayed. Okay. So this one is delayed. This one is not delayed. There are two arms. This one, which pass through the beam splitter, is not delayed, and which reflected from the beam splitter, that is delayed. Okay. When they overlap temporally overlap, then we see this second harmonic. Okay, this second harmonic. And that second harmonic is directly proportional to this, the product of this. Okay. So what we are saying here, do not confuse with the special, it's a temporal. It's a temporal overlapping. Now, these are the terms you must have seen in mathematics somewhere, and it was somehow necessary to show that this is simple Gaussian pulse. Okay, and this is simple. What is going on here? I don't know. Anyway, this is Gaussian pulse, and this is the intensity formula. Okay, and you can this kind of thing. These are standard formulas you can see in any data books of mathematics or something like this. And then if you find out the second order autocorrelation of this intensity, the formula will be like this, and the shape will be like this, okay? And the full width half maximum of this one will be the autocorrelation, okay? And this will provide us the information about the pulse duration, okay? Now, there are two kinds of pulses, standard pulses we consider actually. One is like this, which is called Gaussian pulse, and a second one is like second hyperbolic scare pulse, okay? Shape is almost same, but there is a little difference, and you can see the difference in the formula as well here. And if you find out the autocorrelation, second order autocorrelation, the formula will be like this. It's more complex. And the shape will be like this. Okay. And this shape, the full width half maximum of this shape will give the information about the pulse of the laser pulse actually. So why I added this slide here? Because just you to know there is some mathematics behind it, okay? Otherwise it was not necessary. What we do actually, because we cannot make direct measurement, okay? So we need to do these kind of things. It's mentioned here 1.54. This is 1.54. Okay. And whenever we draw the plot, we have to use this factor 1.54. In case of Gaussian pulse, it is 1.41. In case of second hyperbolic scare pulse is 1.54. Okay. So this factor is important. And why this factor is important, you will see in the next slide. What we see here, time and delay just a minute. You can see me here?
Yes, but the computer say that the recorder is
Yeah.
stopped.
Yes, yes. I stopped it because there's some crash happened here. So to relaunch. Actually, my PowerPoint is it's crashing again and again, so I don't know the reason.
Maybe you are loaded,
Yeah.
that's why.
If you want, you can
Let's
send me the presentation in the WhatsApp, and I can project.
Let me. It's working. Wait a minute. I need to restart my computer. Okay, you people need to wait.
Okay.
Hello. Yes, sir, is in the meeting.
Yes, we are waiting for the instructor. They having some problem with the presentation and the computer.
Okay.
Okay, so where we were actually that okay, so what we were saying about the autocorrelation, what you see here, actually, this is if you see the time and delay. So in general, I mean in time domain, the Gaussian shape is like this, okay? And in case of autocorrelation, shape is like this, but this plot is delay versus intensity, okay? So this is the formula, and autocorrelation and is equal to the, because shape is Gaussian, so 1.41. Okay, so, and this one is full width half maximum of this plot. Full width half maximum of this one multiply 1.41, so it will give you the value of the time here, delay time, and that would be the pulse duration of the pulse. And if you consider this pulse shape, it will be like this, and the autocorrelation signals will be like this. And in this case, you multiply 1.54 with the full width half maximum of this curve. Okay, and mostly we apply this fitting, this one. According to the scientists, this shape is more realistic than this one for the lasers. Okay, so we always apply this one. So when we plot, take the full width half maximum and we multiply with this factor, and this will give the value of the pulse duration. Okay, so this is the autocorrelation. And how it works actually, what you do, let me go back a bit. This is your setup. Okay, so from here we take the voltage values. Okay, and from here we take the time values, and what we do here, these time delay values we plot on this side. Okay, and this voltage is directly proportional to the intensity, and that we plot here. So here is the intensity, there is a time delay, this value, whatever you, and that tau is equal to 2L over C. So we move this translation stage a bit and we calculate this value, and then again move and calculate, and then again move and calculate, and we write all these values here. Okay, in small steps, and we make the measurement for each value, what intensity or what is the voltage output, what intensity that could be. Okay, and then plot is drawn according to that one. Okay, and then we take the full width half maximum. Then we take the full width half maximum here, and okay, full width half maximum. Okay, so multiply this one with 5.14, and that will be the value of your pulse duration. In time it will be definitely, because this is the time scale. Okay, this is how it is done in actual measurement. Okay, so after making this setup, you take the reading for the small changes and make some measurement about the intensity or the voltage level this detector will be connected to somewhere. It can be oscilloscope or can be something else. Then you can use that value on the y-axis and the time value on the x-axis. And the plot will be drawn like this. At certain point, there will be a maximum intensity. At this point is lower intensity. Then again, the intensity will start falling with the passage with the delay. Okay. So then you can calculate this full width half maximum and multiply this one with 1.54, the factor, and that would give you the time, the pulse duration of the laser. Okay, this is the autocorrelation, which is the simplest technique. But this autocorrelation is not providing you the necessary information. It only gives you the value of pulse duration, and that pulse duration may have some plus minus error in this case. But the more sophisticated the technique, which is called the FROG, frequency resolved optical gating. I will not go in much detail of this FROG, because this is a high level kind of things you people may not understand that much, and you people don't need it for this the course. But I give you a little bit idea about, like, only all the arrangement is same, the setup is same. In place of photodetector, we use the spectrometer. And for each delay value, we take the spectrum. For each and every delay value, we take the spectrum. Okay. And that spectrum actually, we make like a matrix. Okay. So there is one value, which is a wavelength, which is same, and the different intensity values from the spectrometers. So we have different plots. And that plot will be in the form of matrix. And then this matrix data is used for certain kind of retrieval software. And that retrieval software retrieve the some information which we cannot get from the autocorrelation. And that is the phase values, pulse duration. I mean, if the pulse is like have some problem, there is a tilt, etc., etc. Okay. So the mathematical formula for the FROG is this one. This is your frequency. This is your time. Okay. Delay time. And it's integral. This is electric field, the actual signal. And you have this overall equation, which is the wave equation actually. And you have this one time delay. As I mentioned that I will not go in much detail because there are so many things in this one. The main theme actually is here that in place of detector, we use the spectrometer and we take the spectrum for each and every delay. And then we'll make the matrix. And that matrix is used with a different kind of software. We call it FROG software. And that FROG software will give the information that is about the phase, pulse duration, etc., etc. And when we make a matrix, when we make the matrix actually, from this matrix, we get this kind of, it's called interferogram, it's images. Okay. If you have a matrix, what is matrix? The values here and some values here, 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 here. And that can be 200, 300 or 1,000 values. Okay. So column and the rows. Okay. That may be like 200 by 200 or 300 by 300. Okay. So even you can see in the origin as well. So this matrix is converted into the image and we can see image like this. Okay. And these images will give you the information that if the pulse is chirped, if the pulse is unchirped or pulse is chirped, is positively chirped or negatively chirped. You can see the difference. If it is unchirped, it's very nice round shape. If it is chirped, then you have like this kind of the shapes. So from the matrix, how did matrix we make that? We take the data for each and every time delay in the form of a spectrum. And that spectrum, like if you take 100 data sets, and then there will be 100 spectrums, and you make a matrix, and then matrix is converted to the image, which we call the interferogram in case of frog. And that images are like this. Okay. And these images are giving you the information. And from these images, you can also get some other information as well. What I skip here, because in case of frog, we always need that spectrometer. So what exactly spectrometer is? Spectrometer take the light pulse, and we use the grating to disperse it, and then the detector to detect it. Okay, like here, pulse is entering, very small slit. Okay, and we have here the collimating mirrors, curved mirrors. Okay, so these curved mirrors, like light is entering from here, light definitely it will spread. It fall on this collimator mirror, then it will go to the grating, and from grating to the other collimator mirror, and then from here to go to the detector where we can see the spectrum like this. Okay, so it's disperse the light, and this dispersion actually, it helps us to see the spectrum of the beam which is entering the spectrometer. Okay, so why it's necessary to show a little bit about the spectrometer? Because the spectrometer is used in the frog setup, in this setup. So if you animate this the spectrometer, there are two kinds of spectrometers. In this one here, we use the reflecting type grating. And here in this one, we use the reflection grating, but it's not a reflecting type, it's a transmission type. So light is passing through. When the light passes through, it disperses. Okay, and then it moves towards the detector, sorry. So here, when the light here, and this is a curved mirror, and then it go to the grating, and then here and here. After the grating, it disperses, and this dispersion, you can see the spread of the light, and it falls on the detector, but we can see the spectrum here. And here the same thing, only we are using the transmission type grating. And what are the grating? The grating is a very sophisticated kind of things. Number of rulings on it, like thousands. And that is why the light is dispersed from these lines on this grating. This is the same thing which I explained already. When the two electric field, delayed electric field and the actual electric field, they overlap temporarily, then we get the signal. Okay, and that signal is similar like in case of frog or in case of autocorrelator. Only difference is that in case of frog, we detect this signal with the help of the spectrometer, but in case of autocorrelator, we detect this signal just with a simple photodiode. This is, I explained again. So here, this animation, you can see this is, if you remember the grating stretcher, compressor. So how the compressor is optimized, and this is the image from the frog. Okay, the matrix data, how it changes with the separation of the, if we change the separation of the grating in case of stretcher. You can see here. So the separation is decreasing, and you can see the difference in the shape. So from here, we can guess at which value of the grating separation, the image is much more smoother and kind of unchirped or something like this. Here you can see again. So that is why we use the frog for optimization of the whole system. Okay, because the grating compressor is one of the important thing. Whether you can optimize the grating compressor or you can optimize the grating stretcher, it depends. Usually we use the grating compressor to optimize the system. Optimize mean to adjust to the minimum possible pulse duration. Now the applications, actually last few slides, there are so many applications. Okay, I don't go in detail of that applications. You have we can generate the coherent X-rays, and this is very common practice in these days. We use when we use the femtosecond ultrafast lasers. Okay, and we can generate the plasma, and then we can study the laser and plasma interaction, and we can use this one in eye surgery. We can use in microfabrication, machining, and chemistry, chemical reactions. What is the chemical reaction to generate the terahertz radiations, and in medicines for the cutting, for the eye operation, and in industry for many other things. So the eye surgery, actually, femtosecond laser especially is used, not the picosecond laser, because picosecond laser can heat up and damage the other part of the eyes. So mostly we use the femtosecond here. You can see in these figures with the help of femtosecond laser here. The flap of your eye is lifting up. Here you can see, here you can see. And this precise kind of precision can only possible with the femtosecond laser. Okay. And why it is like this, you can see, I wrote down here that femtosecond laser, actually, because it's a very short pulse. And so the short pulse mean it can work in a short time, and less heat is generated as compared to the picosecond. Picosecond take a longer time, so the heat spread around. It may damage the tissues around. But in case of femtosecond laser, it's not like this. That is why it's much safer. And so it's without burning or tearing the tissues, okay, because of very short pulse, okay. And also in case of longer pulse, as I mentioned, that heat spread, pulse is long, heat spread, okay, and it damage the issues. So that is why picosecond, even you cannot use a femtosecond. It's more a reliable kind of thing for the laser surgery and the LASIK. What is LASIK can come in the next slide, okay. And so laser assisted in situ keratomyelitis. So to correct your vision somehow, the focusing. Okay. So this is the setup, which is it's not easy to understand because there are many things actually with this setup. The main thing is that to understand that in this kind of technique, which is called LASIK, they correct can correct your eyesight. So glasses can be removed, and there are many cases now in these days. People they have this treatment, and their eyesight is much better. The focusing is adjusted. How it is, you can see here in this animation. Probably it's just a rough animation. When you shine the laser so that the cornea is reshaped with the laser pulses. Okay, so cornea is reshaped. So if the cornea is reshaped, you can see the focus here, it exactly at the retina. We wear the glasses if the focus is here somewhere, and if it is on the retina, we don't need to wear the glasses. Other application is a laser-driven electron acceleration. And that acceleration actually is very promising. rather than to use the huge accelerators, magnetic field and this and that, electric field. You need to make hundreds of meters or something like this. So the laser, with the help of laser, you can do it on the very small scale. And these electrons are not generated directly, but we use some certain kind of gas jet, very small kind of jet, and the gas is filled in it, mostly inert gas, helium or neon, and the laser is made to fall on it. And after this here, like this is a gas jet. Okay. And the laser is supposed to fall on it, focus on it. Okay. And then on the other side, you can see the bunch of electrons. Okay. And that electrons are supposed to be directed somewhere. That is a different arrangement. So with the help of this laser, we can generate the electrons and it can be directed for different applications. These electrons, bunch of electrons can be used. And from these electrons, we can also generate some other atomic particles as well. But that is long story. And here I'm just giving you the little overview about what can be done with this femtosecond laser. So you can see here, this is from here, and you can see this accelerated electrons can be seen. And many people are doing this kind of work in these days, actually, in the many labs, actually. This is one of the hot topic to generate the atomic particles by using the laser, especially ultrafast laser. Drilling and machining is much more convenient, actually, with the femtosecond laser. Even though picosecond is also in ultra-fast category, but the femtosecond is because of the much shorter in the pulse as compared to the picosecond. So that is why it's compared here, and it has much more finer, you can say, the drilling here as compared to this picosecond. And this one, you can see the engraving. Okay. So because of extra heat of these pulses, picosecond pulses, the hole is not very fine. And you can see the other part of there are these parts which are not needed if you make it not a clean hole, actually. So here it's much more cleaner. Here you can see in case of if you animate, actually, the picosecond and femtosecond is much more cleaner. And because of the extra heat, because the pulse is very long, so it generates the heat around it. So the hole is not very clean, especially when you need really precision. So you cannot use a picosecond laser for drilling purposes. And at the last, actually, is the teramobile laser. Teramobile laser, why it's necessary to show in one of the applications. This is a same category of femtosecond lasers. It has a concept of lidar. We can use lidar. We can detect the aerosols, the particles in the air with the help of this one. And we can also use for the remote ignition. And we can also use to direct the lightning from the sky to on the earth by using this technique. So here, actually, you can see here, these all are different parts of the laser system: oscillator, stretcher, amplifiers, and compressor, everything are there. And it's called teramobile because it's in the kind of big container, and you can move it. You can, I mean, wherever you need to do some certain kind of experiment, and the filament is generated. Very high power filament. Filament means that when the very high intensity or very intense laser pass through the air, some kind of ionization happened. And we see that in this kind of filamentation. It's filament, like filament of the bulb or something like this. So that filament is like very hundreds of meters. We can see if the laser is very intense and it's like in joules, hundreds of joules maybe, then you can see that filament here like this here in the air. Okay. And this filament actually, it can be used for different applications. I mean, it can be used to attract the lightning from the sky, and it can be used to ignite something from far or something like this, or as a weapon, you can say as a weapon. So, and it also help you to direct the light from the sky to place where you want to fall it. So it can be used as a tactical weapon actually. How it can be like this, you can see if it is as a lidar to detect something from the sky, and the reflection or the deflection of the laser from the particle you can detect it. And that will give you the information what kind of clouds are there, what kind of particles in the atmosphere, or something. It's called remote sensing as well, using a laser. And for this kind of thing, you need a terawatt laser, definitely. Not a petawatt, because petawatt cannot come in the container maybe, but the terawatt laser. So these are the major applications. And the course is concluded. Okay. And the lecture messed up because of this technical problems, but anyway, it's concluded. So I don't know, if you people are feeling sleepy or something like this.
No, sir.
No, sir,
Okay.
we are fine.
Okay. Yeah. So if you have a question now, or if you want question in the last lecture mean is just evaluation of you people. And so, but if you have now, you can also ask if you have anything in your mind. It's not easy to understand, frankly speaking, for you people, background wise. But if you try a little bit, maybe you can. Maybe some of the people, they understand a bit more. Gazanfar, he left.
Yes, sir.
You must be sleeping now because. So, what do you think, Gazanfar? Now you understand that
Sir, last part,
autocorrelation.
sir, yes, I understand. But the last part of video of this lecture, where we discuss the applications, are a little bit conceptual, and I didn't
Yeah, I
get
mean,
much of that.
yes, I mean, application, I want to give a little hint about it. It's not my intention to explain, because this one is separate course. I mean, the application of the ultrafast lasers, okay? And each
Okay.
and every application has you need to dig out. It's huge things. And people are researching on these things. Okay, so
Sir,
you
I have,
cannot, yeah.
yes, yes, sir. I have one question. It's not one question, it's just the confirmation. Sir, as you mentioned in the when you're discussing about applications, especially the eye surgery, we prefer the femtosecond laser
Mhm.
than the
Mhm.
picosecond.
Mhm. Mhm.
It's just because of the energy.
Not
Picosecond
energy.
have the
What do you mean energy?
peak power.
Not the peak power, actually. It's pulse duration.
Okay.
Pulse duration is important here.
Yes, because the area under the pulse will be gives the average energy, I think, number of the photons.
Mhm.
So
So
the small femtosecond has the small pulse duration, so means the number of photons will be less than the picosecond.
number of photon will be less. No. correct your understanding.
Sir, area under the spectrum is gives the energy, I think.
No. No, that is radiance. That is irradiance you are saying about. That is irradiance.
Okay.
Okay, so correct it. Maybe next time we can discuss. Okay, so any other who is not sleeping now or who is still there?
Sir, I have a little question.
But you are missing
Sir,
your
I
Vedic
have,
ceremony. Yeah, you are still here.
yes, sir, when it is not something very, very important,
Mhm.
then I miss. And to be honest, I don't
Okay,
like a wedding ceremony.
okay, go ahead.
Sir, can you move to the image of beam splitter?
Image of the beam splitter? What do you mean?
Slide backward, little bit. Just this one,
Which one?
this one, this previous, this one
Hmm.
is good.
Okay. Hmm.
Sir, we can see uh, there are two rays splitted. One is delayed and one is fundamental.
Mhm.
There is a point where these two could interact. If you
Mhm.
could see, sir, don't their interaction won't affect each other.
No, this is the characteristic of the crystal. They're supposed to overlap there each other. I mean, interaction,
Sir,
we actually, the thing is that we attenuate. Attenuate means we reduce the intensity of the beam when it enters.
sir, I'm talking about the point exactly below the beam splitter.
No. This is just in the diagram. Height is different.
All right.
This height is different, actually. This is because I'm not showing you a 3D diagram. This is a 2D diagram, so that is why.
Yes.
But even in this case, they can cross each other. It doesn't affect. If you have a
Yes.
clean room, if there is no dust particles.
Yes.
Hmm. Okay, so Salman must have so many questions, isn't it?
Sir, I also have another question.
Okay, go ahead.
Sir, why we use electron accelerator?
There are many applications of the electrons for certain kind of things. We accelerate the electrons and then we study many other things. You know that a free electron laser also exists.
Yes, sir.
And we need the
I
electron to generate the X-ray as well. So there are
yes,
many
sir.
applications. Yeah.
Yes.
Okay, so Mauricio, are you there?
Yes, I'm here.
Okay, so today was the last lecture. So in the next lecture, there will be a kind of evaluation. Evaluation means, I mean, I want to evaluate you people, how much you people understand or
Yes,
whatever.
sounds good.
Yeah. So I'm assuming you will be there.
Yes,
Uh, yeah. So probably you can also ask the questions if you have on that day, or maybe today if you want to ask anything.
Okay. Well, I don't have a question for today, but I just want to thank you, for your dedication and time you give to this course.
No, you're welcome. Actually, it's, at least you people. I hope you people could understand something. And so I think Salman is not here. So Tahura and Arusa Hadi, you people are there or left?
Yes, sir.
So did you understand, I mean, something in today's lecture or like?
Yes, sir. It was interesting, especially discussing the application. I like it very much.
Application side.
It is used in many applications such as eye operation that you discussed in detail. And thank you so much for giving us time and delivering your lectures.
You're welcome. You're welcome. So only intention is to you people to learn something.
Thank you so much.
Yeah. So the Ehtisham, you are there or you are also not there?
Yes, sir, I'm here, sir.
So
Sir,
yeah.
Sir, actually, I was confused about the after the autocorrelation, we see only two beams coming out of the crystal, but in the spectrum we see three. I mean, the second
Because
harmonic
this is a cross.
beam.
There is a cross. So two beams having the same wavelength. This is a crossing. This is a crossing here. So the center one is green one, which is the half of the actual one. These two are out because they are crossing each other.
Okay, thank you.
That is why there are two beams. Okay. So David.
Yes, sir.
So probably, I mean, if you have any question, you can ask. Otherwise, we finish.
Yeah, it's very interesting the last application. I go good in deep in detail.
Yeah, you can dig it in.
Okay.
Yeah. Amna Said.
No, sir, I have no questions. And sir, thank you so much for this course. I was
You're
a
welcome.
beginner and I learned a lot about ultrafast laser.
Yeah, sure. I mean, I hope you people learn something. So probably, but the next, I expect you people to come in the next one.
Yes, sir.
Okay. And Nargas, Ghafoor, you are
Yes,
there?
sir. Yes, sir, I'm here. So thank you for this course. It was really helpful. And today actually, now I can picture the. Basically, I studied autocorrelator and I was just digging in mathematical terms. Now I can get a picture of it.
Yeah, it's
What
good
it
actually.
is and how it is in terms of spectrum, and plus the last part, it was very interesting. I am from since the very beginning of the course I studied about the LESIC, and I even mentioned in my first assignment that was the application I was very wondered of. So thank you for this course.
You're welcome. You're welcome. Okay, so Salman, are you there?
Yes, sir.
Before you were sleeping?
Hello, sir.
I think I asked you many times, but you are not replying.
Maybe, sir.
Okay, I think you are sleeping. So we conclude here. So let's meet next Sunday and try to go through all the slides before to enter in the class. Okay.
Okay, sir.
Okay, so all of you, there are few actually missing today, but I expect all of you to come in the last one and you people to be evaluated in somehow in some matters. And you people will also get some, not in the next class, but later on I will send you the kind of certificates or letters or whatever, whoever finished it. I have to check some of the assignment yet. But in any case, we will meet in the coming Sunday. Okay, so thank you very much for attending this class. And we'll meet in the next class, okay? So meanwhile, take care. Good night and Allah Hafiz.
Officer.
Allah Hafiz. Bye-bye.
Thank you very much, sir.
You're welcome.
Allah Hafiz, sir.